Okay, so this is going to be notes for 3.1 and 3.2. This is going to be all review of things you've already done last year, and some of these things we've even talked about this year. So this chapter is going to be about polynomials and rationals. Today, though, just polynomials. So it says a polynomial function is a function with one or more terms whose exponent is non-negative integer. All right, if we have a negative integer, that's going to give us a denominator with x in it, and that's going to be a rational. We'll get to that later. Okay, let's just go over these words. The degree is the highest exponent. So the highest exponent in this polynomial is 5. We would call this a fifth degree polynomial. All right, leading coefficient, well, that is the coefficient in front of the x with the highest exponent, and so that's going to be 3. You do have to be careful not just to look at the first term, but really look at the term with the highest exponent. It could be hidden in between two other terms over here. All right. These two things right here are going to help you determine in behavior. All right. The constant term, which is going to be the number with no x, this is important because this is going to be your y-intercept every time. Okay. Every polynomial function is a continuous smooth curve, and its domain is all real numbers. So this is nice. It's not something you have to memorize. It should make sense, but it's a nice thing that it will always be that way. The range sometimes will be all real numbers, sometimes it will be other things. So if I ever give you a polynomial and I say, is this continuous? You know that that's yes. It's going to be just a curve. And there will be no asymptotes in a polynomial. There will be no holes or removable discontinuities or anything like that. Okay, end behavior is a description of what happens as x approaches infinity and x approaches negative infinity. So let's think about the graph or the polynomial that I just gave you, and let's think about its graph. As x approaches infinity, meaning as we get really, really big x's, what is the y value doing? Well, it's also approaching infinity, and that has to do with that positive leading coefficient. So we would say f of x is approaching infinity. And that's what's happening to the right. All right? We used to call this rise right. And this is still an okay way to say it, but we want to make sure we understand how to write it in a technical, notational type way as well. All right? So now let's think about what's happening to the left. And this is how we write as x approaches negative infinity. What is f of x approaching? Well, this has to do with the degree. This degree is odd, all right? So what's going to happen is we're going to have a rise to the right here, and then it's going to be an opposite. Think about other odd polynomials like cubics, okay, or lines that are degree 1. That's an odd number as well. There's going to be some business in the middle, but it's going to have an opposite effect, okay? Another way you can think about this is as I plug in a really large negative number, what's happening to the y value? Well, that's going to be a really large negative number, okay? And again, that's another way to explain this is going to be an opposite behavior. What's happening on the right is opposite to what's happening on the left. Now, if you ever forget these rules, and we're about to write them down, and some of you are really good at memorizing, but not everybody is, and it's always good to have an explanation and not just a memory of something that makes no sense. Just think, if I plug in a really large positive number, what is the y value going to do? If I plug in a really large negative number, what is the y value going to do? All right? So let's kind of recap what we said here. If we have a positive leading coefficient, all right, then we are definitely going to rise to the right. Okay. What about if we have a negative leading coefficient? This is different than the one we just did. Okay, then we're going to fall to the right. And I'm using to the right here because we're talking about plugging in a really large positive number. All right. Odd degree. This is the one we just did. Odd degree will cause an opposite behavior. So we would say that it's going to be whatever is happening to the right, it's going to be opposite for the left. And an even degree. Think about a parabola. A parabola is an example of an even degree polynomial we've done lots of things with. Parabolas either look like this or like this. Notice how the behavior is the same to the left and to the right. So we're going to write the same behavior. So let's do a couple of examples and make sure that everybody understands this. this idea of end behavior, I'm going to start using the word limits. And this is really important when we start really applying the concepts in calculus. So I want to make sure you understand this. Okay, looking at the leading term, all right, negative leading coefficient. This means I'm going to fall to the right, or I'm going to go ahead and write this out in the technical notation. If I fall to the right, that means as x approaches infinity, f of x is going to approach negative infinity. All right, let's think, okay, now we have an odd degree. That's going to have an opposite behavior. So for the left side, as x approaches negative infinity, we're going to have an opposite behavior, meaning it's going to be opposite here. So we're going to write positive infinity. All right. Next example, leading term. Make sure that you really are identifying the leading term. Don't just pick the first one. It usually is. But make sure that you identify that correctly. Okay, so what's happening, see if you can do this one on your own. What's happening as x approaches infinity, and what's happening as x approaches negative infinity? And if you get confused by the rules, just go back to how we talked about it at the beginning, which was just plug in. Imagine what would happen if you plugged in a really large positive number, and what would happen if you plugged in a really large negative number. Okay, so as x approaches infinity, we get f of x also approaching infinity. And then this is an even degree, so even if I were to plug in a negative number to the even degree becomes positive again. So that's another way to think about why this is the same behavior right here. Okay, obviously you can graph these on your calculator to check your work. Alright, so now let's talk about zeros. If p is a polynomial and c is a real number, so we're not to imaginary numbers yet, then the following statements are equivalent. C is a zero of p. Okay, then C is also what we call a solution of the equation for p of x equals 0. And this right here is the same as x-intercepts. Okay, but for x-intercept, I'm going to write it as c comma 0. I'm going to write it as the point. So zeros, solution, x-intercept, sometimes we use the word roots, or you did anyway in past classes. Those are all referring to those same values. Now for the factor, a factor is a term. And it's going to be the term x minus c. The reason it's x minus c is because if you set that term equal to 0, what would the solution for x become? Just c. That's why it works that way. Okay, and we're going to use this a lot. These solutions are going to become pretty important with polynomials. Intermediate value theorem. Now this is going to be like a duh. That's so obvious. Why did we have to put it? All right. So intermediate value theorem sounds fancy, but it's really just a very obvious statement. If p is a polynomial and p of a and p of b have opposite signs, meaning one's positive and one's negative. So let's graph out what this would mean. Okay, here's a and here's b. It's not that a and b are opposite. It's that, let's say the point for a is up here, and let's say the point for b is down here, meaning p of a is positive, but p of b is negative. All right, and then the curve could look like this. This is just a sketch. What happened between a and b? Well, while the graph was positive, something has to happen before the graph turns negative, okay? And that's this next part. Then there exists at least one. There could have been many twists and turns right around the x-axis. But there exists at least one value c between a and b for which p of c equals. Now what happens between positive and negative? 0 happens. Okay? So let's mark this on the graph. So here then would be c, and that value. There could be many values. Like I said, this could go up and down, up and down, up and down. But there has to be at least one. So this is useful when we're trying to figure out if there's zeros. Okay? Here c is a 0 and x minus c is a factor. Okay, so let's use all of this information to answer all the questions or the things they tell us to find on 1. So it says, given this polynomial, find the zeros. Well, what we need to do that is to set it equal to 0 and hope that this thing factors. Now, if it doesn't factor, we're then going to have to use the calculator. But Right now we're working without the calculator, so we can conclude that this probably does factor. So we set it equal to 0 and we factor out the GCF. Now I'm going to go ahead and factor out negative x squared so that I can deal with just one negative and not have to mess with it as the leading term here. And so that's going to give me 2x squared plus x minus 3. I can factor this just a little bit further into 2x plus 3 and x minus 1. If you're still having problems with factoring, you have to come to tutoring. This factoring business never goes away. It's always important. Okay, this is as far as I can factor. So what I'm going to do now is I'm going to set each factor equal to 0. And I'm going to actually find the solutions or the zeros. Okay, so this one over here on the right, that's easy. X equals 1. Okay, that's easy. Here you have to do a little bit of work and you get negative 3/2 or negative 1.5. And then this one looks confusing, but it's just 0. All right, and what's interesting about this one is because the x is being squared, I'm going to write the word double here. We could also write that there's a multiplicity of 2. Now this is going to cause something interesting in the graph that you may or may not remember. Okay, we'll get to that in just a minute. Okay, so determined the end behavior. I'm going to write this up here, part B. All right, as x approaches infinity, what is f of x approaching? What is this graph doing to the right? Okay, negative leading coefficient, it's falling, so we write negative infinity here. Okay, what is this graph doing on the other side as x approaches negative infinity? Is it going to be same behavior or is it going to be opposite behavior? And if you've already forgotten the rule, then just plug in like negative 1 million and see if this is going to give you a positive or negative number. Well, this is an even degree, so this should be the same behavior. You get the same result just by plugging in a number. All right, so then C says sketch a graph. Okay, when you're sketching a graph, it is a true sketch. It's not going to be very accurate, but you should always start by plotting these points. Okay, so I have a point here, an x-intercept at 1. I have one here between negative 1 and negative 2, and I have one at 0. And if you could find a y-intercept, you would plot that as well, but in this case, I know my y-intercept has to be 0, and that's obvious from the beginning graph anyway. Okay, now let's think about, in fact, I'm going to switch the color back. Now let's think about how we can do the right behavior. If this graph is falling to the right, I can do that. And if it's also falling to the left, I can do that. Now, remember that for multiplicities, even multiplicities, okay, the graph will not cross through at 0. It will actually just bounce off. That's called tangency. All right, but the other roots, it is going to cross through. Okay, so notice that it crosses through these two zeros, these two x-intercepts, but at 0 because this is squared here. It doesn't cross through. It's a tangency. All right? You might have questions about that. You studied it last year, but you still might have questions. You know, bring those questions to class. Okay, so this one's more complicated, but it's already factored. So the nice thing is that we already know what the zeros are. We can just set this equal to 0 and think, okay, if I set x to the 4th equal to 0, I'm going to get x equals 0. That's 1, 0, and it has an even multiplicity again. That means that the graph is not going to cross through at 0. It's going to bounce off. It's going to be a tangency. Okay, if I set this term, x minus 2 cubed equal to 0, I'm going to get x equals 2. But this multiplicity is odd, so you don't even need to write that because that means it's just going to behave like a regular root. Okay, the last one, x plus 1 squared. We get x equals negative 1. And this, again, has a squared. It has an even multiplicity. There's lots of things in math where you talk about even and odd, and this is one of them where that really makes a difference. Okay, and the other thing we need to consider is what would be the leading term. We don't need to multiply all this out, But if I were to multiply it out, what would be the leading term? It would be positive x to some power. You can actually just add these numbers up, okay, using like our exponent rules, and your leading term would be x to the 9th, and I don't really care what comes after that. That's going to tell me what's happening to the right and to the left. Okay, so let's put all of this on a graph. And again, this is just a sketch. Okay, so I have a root at 2, I have a root at -1, and I have a root at 0. And to the right, positive means I'm going to rise. Odd degree means that the left is going to be opposite. Now we just have to fill in the middle. So let's just start here with -1. That was an even multiplicity, so it's not going to cross through. It's actually going to bounce off, but it's got to come back up and now hit this root. Okay, 0, also an even multiplicity, so again, not cross through. And then notice what happens at 2. It's just it does have multiplicity, but it's an odd number, okay? It's odd, so it just behaves like a regular root. So we didn't even have to write that down. Okay, you can check this with your calculator, and we're going to practice this in class, so please bring your questions. All right, now we can see that on all these we had some terms. We had some local mins and local maxes, and in the last chapter we learned how to find those in our calculator. All right, but you can actually determine the number of local extrema just by looking at the degree. All right, so for a 4th degree polynomial, you will have 3. All right, we used to call this the maximum number of turns last year. All right, for the next one, if the degree is 5, there will actually be at most 4 turns. So what am I doing each time? Looking at the degree, and I'm subtracting 1. So how many turns or number of local extrema would there be in C? There would be 3. Now when you actually graph these, it may appear on the graph to have less than this. And this is why we say there's at most n-1 local extrema. Okay? And that's because of the whole multiplicity issue. Things can change in the graph, and the graph cannot appear to have that many maxes and mins. All right, now let's do 3.2. I'm going to spend a little bit, I'm not going to go through this and teach it to you like this is, again, this is review. All right, so long division was really difficult last year. Hopefully you find it to be much easier the second time around. Remember, for long division, okay, you set it up where the denominator goes into the numerator. Now if there's any terms that are skipped, like in this problem, the cubed term is being skipped, so I have to write that in as a 0. This is to keep everything nice and neat and lined up. Okay, so now let's try the first step. See how much you remember. 2 goes into 8 4 times, and x squared goes into x to the 4th x squared times. Now here's how you can check if you did this right. When you multiply, which is your next step, you should get exactly what you started. These two terms should be the exact. If they're not, you did it wrong. Okay, let's keep multiplying. 4x squared times negative x, that's negative 4x cubed. 4x times 2, that's 8x squared. Okay, now I'm ready to subtract, and when you subtract, you're just going to switch all these signs. All right, we have 4x cubed minus 2x squared, and then we bring down. Remember, that's the last step in long division. Okay, I'm going to switch colors, and we're going to do the next step. 2x squared factoring into or going into 4x cubed, that will be 2x. Notice that I went down 1 exponent. Okay, now we multiply. 4x cubed minus 2x squared plus 4x. That's a 2. And then subtract. Always the first term should cancel. This time we got lucky. The second term canceled. This is going to give us one less step. All right, now I can't go any further, so this is what we call our remainder. So what we're going to do is we're going to write plus negative 7x plus 1 over whatever you were dividing by, 2x squared minus x plus 2. Now this did not divide in evenly which means that the denominator is not a factor of the numerator. Okay, let's talk about synthetic division now. Synthetic division usually people like better and remember better. Remember, you can only do synthetic division when you're dividing by something simple like x plus or minus a number. Usually we call this x minus k or x minus c. And if we're trying to divide by x minus 3, then actually we're going to do synthetic division with the 0, which would be 3. This is almost like using like a 0 test. Okay, now let's plug in the coefficients. You don't use the x's in synthetic division, but remember that if any terms are skipped, you have to put a 0 in, and this is mandatory. You will not get the right answer if you don't do that. Okay, for synthetic division, remember the first step is to bring down, and now you do the process of multiply and then add. And then 3 times 1, multiply, add. 3 times negative 3, multiply, and then add. And in this case, the way you read this framework is to start on the right. That's your remainder, that's your constant term, that's the coefficient of x, and here's the coefficient of x squared. So my answer is going to be 2x squared minus 1x, or just minus x, minus 3, and then minus 4 over whatever you were dividing by, which is x minus 3. There we go. Okay, remainder theorem says if the polynomial p of x is divided by x minus c, then the remainder is p of c. So let's use that on this last example. Okay, if I call this f of x, then right now I know what, not p, what f of 3 is. What is f of 3? Without plugging it in, it's going to be your remainder, negative 4. This is nice to determine if something is a factor without having to go through synthetic division. You can just plug in the number. Now in this case, probably synthetic division is easier to do than actually plugging in a 3. Sometimes it's easier to do synthetic division, sometimes it's easier to plug in the number. Alright? Factor theorem kind of goes along with that. These two are usually used in conjunction. So if c is a 0 of p, that happens if and only if x minus c is a factor of p of x. So what I want to ask you is x minus 3 a factor of f of x? No, because the remainder was not 0, and it didn't divide in evenly anyway, so we'd know it because of that. All right, so let's look at number 3. This is asking us a question. Now, normally when you see something like this, you would want to plug in negative 2, and that is how you could find the answer. But now we have this other thing called the remainder theorem that may make this easier. All right, we're going to use negative 2, and we're going to do synthetic division. You kind of have to just use your brain and think through, will it be easier to plug in the number, or will it be easier to do synthetic division? Now notice again that I had to put a 0 in. That's because the x squared term was missing. And we go through this process of bring down, and then you multiply, add, multiply, add, multiply, add, multiply, add, multiply, add. Okay? So you would just say that this is the remainder, this is the constant, x term, x squared, x cubed, x to the 4th, but really what we're focusing on this particular problem is 5. That is the answer. P of negative 2 is 5, and you could go ahead and do that the other way, you'd still get 5. Is negative 2 a 0 of p of x? No. Is x plus 2 a factor? No, because the remainder is not 0. That's what you're looking for when you're answering those types of questions with the factor theorem. All right, number 4 is a question like it, but it's asked a little bit differently. Is x minus 1 a factor? If so, you use it to completely factor f of x. Now, we can actually, just to answer the yes-no part, we can find out what f of 1 is. Notice again that I switched the sign there. And if I plug in a 1, I get 1 cubed minus 7 times 1 plus 6. Now, if this equals anything but 0, the answer is no. It does end up being 0, so the answer to the first part is yes, and we're going to have to do synthetic division anyway. But this could have saved you that step. Again, notice the 0 because there's no x squared term. And so we bring down the 1, we multiply, we add, we multiply, add, multiply, add. And again, notice that the remainder was 0. This is what we wanted. And you interpret your answer by doing constant x squared. And I'm doing this because they say use this to completely factor the problem. All right, so this is one factor. All right, don't forget about your other factor. My other factor was what I already had divided out, so I'm going to write that off to the side. And if you can go further, you would want to do that, and I can here. I can say that this is the same as x plus 3 times x minus 1. I'm sorry, x minus 2, and then x minus 1. And you could check your work here by hand or with the calculator. And from here, you could then sketch the graph. So with just a little bit of help, a hint on what the first factor would be, we can factor it further, whereas we don't really know how to factor this on its own. We can sketch the graph. There's a lot more things we can do now in terms of graphs without a calculator, okay? And this, I promise you, if you can graph without a calculator, it will help you next year. So this is why we practice this stuff, okay? Bring your questions to class. I know that you have them. Come to tutoring. If there's some of these things you just didn't learn at all last year, you need to come to tutoring because this is supposed to be review.